All right. Oh, it's week 7. Every time I put these slides up and it tells, I write like what day it is. It's week 7, Monday. So I know week 7 is kind of always it's like the tipping point where weeks 1 through 6 you were juggling things and things are starting to, staying afloat. But week 7 is like, you gotta be on your game, otherwise everything's gonna start coming and crashing down. So that's not like not a threat, okay? just
a friendly warning.
just me remembering, because my entire undergrad and actually grad school experience was always quarter system as well, so I don't understand these semester people. Although, like, I did teach like a quarter at a semester school, and I was like, what? This is dragging on forever. But so I'm accustomed to the fast pace of it all. But yeah, week 7. So things, we just have a few weeks remaining, and we'll go. How's the homework coming along? Okay. All right. Well, it's intended to be a challenge, but a fun one. I guess we all have different definitions of fun. So hopefully satisfying. If you can't figure it out, that's okay. All right, do as much as you can. I'm sure you can get a few things in, right? Like land on go to jail and you get sent to jail. Some of those things. Encoding your chance deck should be hopefully relatively straightforward. You just basically, if your space is one of these spaces, draw a chance card, right? Okay. Anyway, Andrew will go over a little bit in discussion, and hopefully it will go on. Okay. So we've had a thorough discussion. I don't know about thorough, but we talked a lot about floating point numbers. And so now that we've gotten all of that away, and you understand there are just inherent limitations to how we store numbers in the computer, now we can start talking about numeric methods. Okay? And so a numeric method is a technique or algorithm that allows us to get approximate solutions to mathematical problems. A lot of these things are iterative methods, and we use them with computers because computers are good at doing calculations iteratively and quickly. Okay? They're not good at this analytic thinking, but you can, if you just need an approximate answer, computers are great for that, right? So, why would we want to do this? Well, sometimes you have a math problem and it doesn't have an exact or analytic solution that you can arrive at using either algebra or calculus, or maybe it does exist, right? Even if an exact solution does exist in theory, it could be computationally intractable, right? It could be really, really, really hard to get, or it could take an unreasonably a lot of computing power just to get kind of this thing, right? It's kind of like, what is the exact area of a circle? Okay, that would require, you could specify it in terms of pi, but if you wanted it in decimal, you can't do it, right? But we've all settled and we just say, okay, use 3.14 or 3.16 or 3.159 and however many decimals you want, and then you get an approximate answer, and that's good enough, right? You can use slide rulers. I don't know if you guys even know what a slide ruler is, but it's like before the calculator, you have these rulers that use logarithms to do multiplication, and that's good enough to get you to the moon, okay? So approximate answers, pretty good. And so we're going to take the computer's solution here, right? Okay, so classic example from statistics is you've got your normal PDF. Sorry, this is cut off over here. Okay, I don't know how to use, I don't know how to resize my window. I do, but I don't feel like doing this. Okay, so you got your standard normal PDF, and then if you wanted to get the CDF, right, your cumulative distribution function, are you taking 100B now, or you've already taken it? Okay, You're taking it next? Okay, well, somebody should tell you, like, you can't do this integral, right? It's not possible. There's no closed form solution to this integral. So, but then you go to your computer and you need to get the CDF, right? You use qnorm. You type in qnorm something and it gives you something, right? qnorm 1.96 is what, 0.97500 something. And then, and you want this. So how's the computer doing this? It's not trying to calculate an integral. There's this old Fortran function, specfun, okay? And it does an approximation. It does an approximation to the cumulative distribution function, and it's precise up to around 16 decimal places of precision, and that's good enough for us because that's about as precise as we can get with floating point numbers anyway. Okay, but it's not the actual value. It's just an approximation, and it does it quickly, and we're okay with it. Okay. So today we're going to introduce kind of this first set of numeric methods. These are called root finding methods, and basically we use this function to find approximate roots of a function. So root is basically where the function is equal to 0, where it crosses your x-axis. Right? So you think of some function that takes real numbers as inputs and it returns real numbers as outputs. And a root is basically the solution for where it's equal to 0, and graphically it's where it crosses the x-axis. Okay, and a lot of kind of mathematical solutions can be done here. So one simple method that you're probably familiar with for finding roots is the quadratic formula. You just you have a parabola and you want to get the roots of this thing. Okay. And you just plug in, okay, negative b plus or minus this, and this will give you the roots of a polynomial. Before I go on, we should just say if there is an analytic solution and if it's easily found, use the analytic solution. Don't use an approximation or a numeric method if you don't have to. And so, but anyway. If you can't, then that's when you should use it. All right, so I'm using basically chapters out of this textbook, Introduction to Scientific Programming and Simulation using R, and I believe it's linked in your syllabus, and you should be able to access it. Also, these notes have given this. All right, let's talk about fixed point iteration. Fixed point iteration takes advantage of a function's fixed point, okay? So a fixed point is not a root. A fixed point is a solution to g of x equal to x, right? So if you have some function g, a fixed point is basically you plug the number into the function and you get that number back, right? It's basically where the function crosses the line y equal to x. And so the useful feature of this thing is that once you arrive at a fixed point, you can keep applying the function and you just keep getting the same value itself, right? So, so we have that. Some fixed points are known as attractive fixed points, okay? Attractive fixed points. And fixed point iteration takes advantage of the existence of an attractive fixed point. And that is if you have some value x, as long as x is close enough to some value to the attractive fixed point a, then when you take x and you apply g of x, you get a new value, and you apply g to that result, g of x, and then you apply g to that result, g of x, and you keep applying the function over and over and over and over to itself, it converges to some value a, okay? And I'm not going to, this is like a little bit of a formal definition of it, but don't worry, I won't test you on this, okay? A more formal definition would be that g super n of x, that is, we're applying the function g n times, okay? We're going to say an attractive fixed point a is attractive if there is an interval I such that around a such that basically for as you apply g of n to this, it's going to, whatever the results will be within the interval that we've defined for all n greater than 0. And as n goes to infinity, this thing is going to go to some value a. And so a very simple example of this, sorry, I don't know what's going on with my audio. Simple example of this is the square root function, okay? And you can start off with any number, and you take the square root of it, okay, I guess any positive number, okay? You take the square root of it, and then you take the square root of that number, and you take the square root of that number, and you take the square root of that number, and you keep applying the square root function, it will eventually converge to 1, okay? And this is going to be any value, whether it is just slightly bigger than 0 or very, really, really large number. And so do I have the calculator here? Oh no, how do I? I don't know how to grab this calculator behind the, okay, all right, I guess we'll just have to make it really big. Okay, so I can just type in some really big number, right? I take the square root, and this says it's 3 million something. Square root of 3 million something is 1,778. Square root of that is 42. Square root of that is 6.4. Square root of that is 2.54. Square root of that is 1.59. And then I keep applying the square root, and we get closer and closer and closer to 1. Okay? You can go kind of the opposite, 0.000000001. All right? You take the square root, and it gets closer and closer to 1. Approaching from the other side, we get 0.999999 something. Eventually, we'll get to 1. So, whatever number you want to put in there, take the square root. You get attractive fixed point at 1. And so how does this work? Okay. Well, the way fixed point iteration works, okay, you just you start at some initial value x 0, and then you compute g of x, and then you just repeat it, okay? And to kind of so this will help us find if there is an attractive fixed point. How do we find the fixed point? All we do is we just keep plugging the number into the function itself, and this will eventually get us to the attractive fixed point, assuming that an attractive fixed point exists. And to kind of avoid iterating forever, we're going to just say if the difference between the current value and the previous value, xn and xn minus 1, x at time n versus the previous value, x at time n minus 1, if the difference between that, the absolute value of that difference is less than or equal to some user-specified tolerance, so maybe like 10 to the negative 5 or something, some small value, then we'll say, okay, that's close enough. It hasn't moved much. We'll call it a day. And so here is, let's try to find the attractive fixed point of the square root. And what happened here? There's a huge space. Okay, so I start off at 10. Here's our function. The square root of 10 is 3.16. This is the line y equal to x, 3.16. So now at the next iteration, we will start at 3.16. We take the square root of that. That takes me to 1.778. The next iteration, I start at 1.778. The square root of that is 1.333. Square root of 1.333 is 1.154. And we keep going. After around 15 iterations, I'm at around 1.0007. And then at some point, I can just say, all right, the difference between this value and the previous value, it changed less than, say, 1/100th of a 1/100th, some whatever value, 1/1,000,000th, and you say, okay, that's close enough. So we can take this strategy and apply it to root finding. Oh, before I forget, let me go ahead and give you your first view quiz answer for today. First view quiz answer today is C. C as in cat. C as in cat. Okay, so how can we use this fixed point strategy? Okay, again, we have to assume that a fixed point exists, but how can we use this fixed point strategy to find roots of a function, right? So let's say there's some function f of x, we want to find the roots of f of x. Okay? What we're going to do is we're going to define a different function, a different but related function called g of x. And we define g of x in such a way that when we find a fixed point of g of x, the fixed points of g of x are equal to the roots of x, or of f of x, sorry. Okay, so we define g of x related in such a way that when you find the fixed points of g of x, they will be the same as the roots of f of x. Okay, so when g of x equals x, we want f of x equal to 0. So one possibility is this. G of x is equal to x minus f of x. All right, so this is just, there's lots of ways you could do this, but this is one possibility. And you can see that f of x is going to equal 0. That means we found a root of f of x when g of x equals x. So when we find a fixed point of g of x, that will be the same location where f of x is equal to a root. Okay? And so what we do is we find the roots of f of x by finding the fixed points of g of x. And finding the fixed points of g of x is simple because all you do is just repeatedly, iteratively apply the same function over and over and over itself. Okay? Lots of ways to write f of x equal to 0 as g of x equals to x, and some are going to work better than others. Okay, so let's say we want to find the root of this function, log of x minus e to the negative x. Log of x minus e to the negative x. And we want to find the root of this. We want to find where this function is equal to 0. Okay? So one way to do this is we want to say, okay, well, let's find, we want to figure out, how can we find fixed points of this? So there's, again, lots of ways you could do this. One is, let's say, let's solve for x. Let's solve for x. So I'm going to do log of x is equal to minus e to the negative x is 0. I add e to the negative x to both sides. I'm going to raise both sides to e to the x. And so now I get x is equal to e to the negative x. Right? And so now if I say, well, if g is equal to this thing, then when g of x is equal to x, that's going to be at the same location where f of x is equal to 0. Right? And so if I can find fixed points of this thing, e to the negative x, then I will have successfully found a root of f of x. So that's one possibility. Okay? And so how do we do this? Here, I'm going to just define my function, g, as e to the negative x. All right, that's this function. And then all I do is I'm going to just repeatedly iterate and apply the same function over and over and over again. So I'm going to just start off at some arbitrary value 10, doesn't matter. And then we're going to say take this old value, apply g to it. This will become our new value. We'll just start off and just say iterations is equal to 0. My tolerance level will be 10 to the negative 8. So I want to get at least to 8 decimal places of precision. And so this is my loop. While the difference between the old value and the new value is greater than the tolerance, or the absolute value of the difference between the new and the old value is greater than the tolerance, just run this loop over and over again. Take the new value, make that the old value, apply g to the old value, and that's going to be your new value, and then we want to just see how many iterations this took, so we'll increment iterations by 1. Right? So this is a very simple algorithm. We're just applying g to the same value over and over and over again, and we're just doing this in a loop. Okay? All right. Now, there is a possibility that this runs forever, right? If this is not going to converge, it's always good to have an option for just stopping the algorithm after a specified number of iterations. So probably we want to insert a little fail-safe where it's just going to say if iterations goes over 10,000, break or something like that. Okay, but this, luckily that didn't happen. So this code works just fine, and so I run it, and the result says 1.3.098 is my approximate root, and we'll test it out. If I plug in 1.3098, log of that minus e to the negative x of that, I get something close to 0. I get 9.7 times 10 to the negative 10. Okay, and it took me 19 iterations to reach that value. So seems like it's working. Okay. How does this work? Okay, if we assume that the fixed point iteration method does converge, that is that x at time, if we set x at time n plus 1 equal to g applied to the current value at x time n, and we assume that that xn eventually converges to a, then we can show you that the value that it converges to is indeed a fixed point of g of x. All right, and so here's just we're going to say a is going to be the limit as n goes to infinity of x at time n plus 1, and we're going to just say, okay, well, this thing is x at time n plus 1 is defined as g applied to x at time n, and so the limit as this goes to infinity is going to be g applied to the limit of whatever the value of xn is, and we say, well, we're assuming that xn converges to a, and therefore g of a equal to g of a, that a is going to be a fixed point of g, okay? But that's under the assumption that this fixed point even converges, okay? So if the fixed point method, iteration method does converge, it does converge to a fixed point, but does it always converge? And the answer is no, okay? It doesn't always converge, okay? If the fixed point is attractive, that means initial values are relatively close to the fixed point, and the fixed point iteration method is guaranteed to converge, but not all functions have fixed points. Not all fixed points are attractive, and fixed point iteration is not guaranteed to converge. A sufficient condition is that if you take the derivative at the fixed point, as long as that derivative is less than 1, as long as the absolute value of the derivative at that fixed point is less than 1, it will be an attractive fixed point. But if it's greater than 1, it will be a repelling fixed point, and fixed point iteration will diverge. What does this even mean? Okay, so here's an example of a diverging fixed point. So again, we said there's lots of ways to find some function g of x so that when g of x equals x, f of x equals 0. So one way is I can say, well, here is log of x minus e to the negative x. We'll set that equal to 0. Let's add x to both sides. Okay? And then what we'll do is we'll set g equal to this function over here. And we can say, well, when g of x is equal to x, that's going to be when f of x equals 0. Right? So we say, okay, well, this function could work. And it's true. If g of x equals x, that will be when f of x equals 0. But if I try, so here's my fixed point iteration code, and I put in a little warning, or not a warning, but a failsafe, where if the number of iterations goes over 1,000, we're going to stop the loop, just so we don't run forever. Okay? So same thing, just keep applying g applied to whatever the value of x is, and update our value of x. And we're going to just say if the iterations go over 1,000, we'll break out of the loop, just so it doesn't run forever. Okay. So what happens when we do this? Well, it finds x to be 7,830, and when I plug this value into the function, log of x minus e to the negative x, I get 8.96. That is not anywhere close to 0. And we say, okay, well, and it quit after reaching 1,001 iterations. So that's we reached our iteration limit, and it would have kept going forever if we didn't tell it to stop. So that's a diverging fixed point. And so lots of ways to do it. Some of them are going to work, and others aren't going to work. Okay, and it's a little bit of kind of early on. It's a little bit of trial and error. You can kind of use this principle that g prime needs to be less than 1 for it to be an attractive fixed point. And so we can see that, just kind of by looking at this, we can see that the derivative of this is going to be greater than 1. But yeah, I mean, probably in most circumstances, it'll be hard to find the derivative, just because if you can find the derivative, chances are it's not too hard to find the root in something like that. Okay, let me introduce Newton-Raphson method for finding roots, and let me give you your second view quiz answer. Today's second view quiz answer is D. D as in dog. D as in dog is our second view quiz answer. All right, fixed point iteration is considered to be relatively slow, as the approximation error is usually divided by some constant factor. And so there are faster methods, and a very well-known one is the Newton-Raphson method. And the idea behind the Newton-Raphson method is that we're going to use a tangent line, and a tangent line is basically your best linear approximation to the function near that point. And we're hoping that this is going to work to find a root. So this is how it goes, okay? Let's say a is some root of the function f, and we're going to assume that f is continuous and has a derivative, okay? And it's differentiable. And we're going to just say, let's start with some value x0. This is going to be our initial guess for the root, a. And so the linear approximation is equal to the tangent line, which is the value of f at x0, plus basically, this is like point slope form, the slope at x0, times, the location, how different you are from x0, x minus x0, right? And the reason why this works is if you think about your Taylor series expansion of the function at any point, which is, you can show that as long as you go off to infinity, you can get the whole thing. Basically, we're just taking the first two terms of your Taylor expansion, and it's going to be kind of the linear component, right? And we're just dropping everything with a higher order term. And so the tangent line is a good approximation for this. And then what we do is we say the next guess for what the root is going to be where the tangent line crosses the x-axis. Okay, so the way this picture works is, so here I've got this function, x squared minus 3. X squared minus 3, it's going to cross at the square root of 3 here. But we're going to say, okay, let's start off at 10. What's the tangent line at 10? It's going to be this dotted red line. Takes it down to 5 point something. And then we're going to say, okay, let's plug that in for our next iteration. Okay, what's the function at 5 point something? It's around 25, a little bit less than 25. We take the tangent line there. That takes me down to over here, 2 point something. Okay, and then I plug that in. And then I say, okay, what's the function there? And then we find the tangent line. And we trace that tangent line down to here. And we keep going. And after a few iterations, I'm at 1.956, and that's pretty close. That's pretty close to the solution. Okay, so not quite, but we can keep going, and we'll get our answer eventually. But this is how Newton-Raphson method works, right? And we're starting off with this terrible location 10, where if I plug that in, the original value is 97. 10 squared minus 3, 97. That's not anywhere near a root, but it converges fairly quickly here. Okay. So how do we find what this next value is going to be? How do we find what the next value is? So if you think about what your slope is equal to, it's rise over run. And so we can find the value of the rise very easily, right? We just say, okay, well, you just plug in f at x0, right? You plug in your function value x0 into the function, and you get 97. That's my rise. Okay, and what is the run? Well, okay, so if slope is rise over run, then run is going to be rise divided by the slope. Okay, so we do run is equal to rise over the slope. So the rise is 97 divided by the slope of 20. That's this. And so my next iteration is going to be 10 minus this value, 4.85. So this next value is going to be 5.15. Okay. So if we do this, this can be found as you take your current value x0, which right now is 10, and then we subtract off the rise, which is f of x0 divided by the slope, and this is going to be kind of the quantity of the quote run as far as your traditional definition of the slope. Okay, so you have f of x0 divided by f prime of x0. Okay, and this is going to be your next value, the value at your next iteration x1. Okay, and if we repeat this, then the value for x2 is going to be your current value x1 minus f of x1 divided by f prime of x1. And if we generalize this to just any time n and the next iteration n plus 1, it's going to be this. Okay, and so this is known as your Newton-Raphson method. And so you just start off with some value 0, and then you're just going to repeatedly apply this algorithm, and we will say we have reached some approximate answer, x of n, when we plug in f of xn, it's less than some tolerance level, right? So this is so e being something small value, like 10 to the negative 6 or 10 to the negative 8 or some small value, okay? When this gets close to that value, so something close to 0, that's when we'll call it a day. So let's try it. Okay, so here's our same function from earlier, log of x minus e to the negative x. This requires us to find the derivative. So the derivative of log of x is 1 over x, and the derivative of e to the negative x is e to the negative x. We apply the chain rule, negative 1, and so it becomes plus e to the negative x. So this is my derivative. And so now, to apply this, as far as the math goes, we have our function f, log of x minus e to the negative x, and then we have f prime, 1 over x plus e to the negative x. And so I'm just doing this. I could have done x old and x new, but we're going to just start off at x equal to 2. My tolerance will be 10 to the negative 8, and we're going to just say while the absolute value of f applied to x is greater than some tolerance thing, we're going to keep going, and we'll just take a current value x, subtract off f of x divided by f prime of x, right, which is what we said here, x minus f divided by f prime of x. And we'll update x, we'll increment our iterations, and we'll let it run, okay? And so we let it run. We start off at 2, and it says, okay, your approximate root is at 1.3098. And what value does it give? It's something on the order of 10 to the negative 9. And it took us only 4 iterations to get there. Okay, so that's pretty good. 4 iterations. This slide, I don't feel like reading this. Man, okay. Basically, if we just say, if f is differentiable, if it is continuous, then we can write this without kind of issues here. We can just say, as n goes to infinity, where does this thing converge? Okay, well, we're under the assumption that it does converge. Okay, so if we're assuming that it converges, where does it converge to? Okay, well, when you apply the limit to this, okay, the limit of xn as n goes to infinity, that's going to just go to a. And then you apply the limit to each of these things, the limit as n goes to infinity of this is going to be f of a. And the limit of this is also going to be f prime of a. And indeed, that's exactly what we're saying, okay? So assuming that f prime of a isn't equal to plus or negative infinity, and that f of a is indeed a root, then if the Newton-Raphson method converges, then it converges to a root, okay? But does the Newton-Raphson method always converge, right? So this is also, the derivative has to be finite, okay? But does it always converge? And the answer is it does not always converge, okay? It can be shown that if f is well behaved, all right, meaning that, that the derivative is not equal to 0, and that the second derivative is finite and continuous, and you start at an initial value that is close enough to a, then it will converge quickly, okay? And most of the time it converges quadratically, but these conditions aren't always satisfied, and the Newton-Raphson method is not guaranteed to converge at all, okay? And so these are some reasons why Newton-Raphson method will fail to converge, and we even have some animations to kind of show this. So if this happens, right? So as you're iterating, so it's totally fine if f prime of x equals 0 somewhere, okay? As long as in your iterations you don't encounter that point, okay? So, right, so when you do x squared minus 3, we found the root quite easily, okay? But x squared minus 3 does have a spot where there's 0 slope, right? At x equal to 0. There's it's a local, or it's a global minimum, and so there's 0 slope. That's fine, okay, as long as we don't try to go there during our iterations, okay? So then, but if you do encounter this, if one of your iterations takes you to a point where you have 0 slope, then the tangent line is going to be horizontal. It's not going to cross the x-axis, and it will just break, right? Because you're basically trying to divide by 0, and that's going to break, okay? But even if it doesn't exactly equal to 0, if it just comes very close, where the slope is very close to 0, you know, where is it going to cross the x-axis? It might it might rocket off and cross at like x equal to 1,000,000 or someplace like that, right? If you have a slope that's not 0 but very close to 0, you can end up with something like that, right? Convergence will depend on your initial guess. If it's too far from the starting root, it might not converge at all. It might converge to a different root. Sometimes you can get stuck in a cycle, right? And the Newton-Raphson method is not going to converge, okay? If the second derivative is infinite or undefined at the point, it can also cause non-convergence. And so here is some examples of this. So here's like well-behaved. This is a Newton-Raphson method. So this converges nicely, okay? But here is one. So here it's going to go here, and it comes here, and it goes here, and it comes here, and then it comes here, and then it ends up. The root is over here, okay? But it gets tripped up because we don't exactly have a root here, but the slope kind of changes directions, and so it kind of oscillates back and forth. And it's like trying to find a root here, but there's no root at this location. And then finally, it gets to a root over here, okay? So that could happen. It still finds the root, okay? This comes over here, and then it runs into some issue where you get basically a slope that kind of explodes. Or, well, actually, that one works. But over here, this one doesn't converge, right? This you end up getting this weird scenario where the slopes kind of rocket off here. Okay. So it actually ends up going off to infinity. So you have, all these different kind of scenarios where you don't always find a root. How many view quiz answers have we given you? 2. Okay, let me go ahead and give you your last one. Last one is A. A as an apple. A as an apple. I might run out of time here. So Newton-Raphson method, we like Newton-Raphson method a lot, but one issue is that to use Newton-Raphson method, we have to figure out the derivative, right? We have to figure out what that function is for the derivative. And we have a few workarounds to this, okay? So if you can't find the derivative analytically, there are ways to approximate your derivative numerically, and we can talk about that later. But another method that just says, well, you know what, I don't even want to bother trying to figure out the derivative. We can use the secant method, okay? And the secant method basically says, instead of figuring out the derivative, I'm going to just draw what we call a secant line, okay? And so instead of figuring out the tangent line, we're going to start with 2 initial guesses, an x0 and an x1. So it requires a little bit more computation because you got to plug in f of x0 and you got to find an f of x1. And then you find these points, x and f of x0, and then x1 and f of x1, and you draw just a straight line that connects these two. And that's going to be a straight line that's kind of, but not exactly, like the tangent line. All right, so here's kind of an illustration. So this is not the tangent line. This is a secant line. I started off with x0 equal to 10 and x1 equal to 8. And we're just drawing a line that connects these things. And I follow this line down until it intersects the x-axis. And I say, okay, that takes me to here. And now I'm going to draw a secant line from x1 to x2. Okay, and so I draw a line from this dot to this dot, and that takes me down to here. And then I say, okay, well, here's this location, and we go from here to here, and so on and so forth, and we would trace this. Okay, so the path that it cuts is similar to Newton-Raphson, but no tangent lines were found. And it's not necessary to find the derivative or the slope. Okay, you just, I mean, not the slope. You don't have to find the derivative. Instead, you're just kind of drawing some kind of line here. So the slope of the secant lines is going to be basically your change in y divided by your change in x. All right, so you say f of x1 minus f of x0 divided by x1 minus x0. So this is going to be the slope. And then once to kind of solve for the next value, then you say, okay, y minus f of x1 times the slope m times x minus x1, and you solve for that. And so the next value is going to be kind of your second starting location, x1, minus the value at f of x1 times 1 over the slope. And so the next value we get is 4.611. Okay, and so plugging all of this in, okay, so to kind of generally apply this, we can say the slope of the secant line is given by this function. And to solve for the next thing, we got in point slope form, we have y minus this times m times x minus this. And what we want to do is we want to solve for the next value of x2. Okay, so I've got this, and then we're going to say, okay, we're going to take our next point, x2. X2 is basically where it's going to cross the x-axis, where y is equal to 0. And then we solve for this. And so solving for what x2 is, if you follow all the steps of the algebra, you're going to get x1 minus f of x1 times basically the change in x divided by the change in y. So it's kind of like 1 over the slope times f of x1. So there's a lot of similarities between this and Newton-Raphson method. It's just, instead of doing f of x1 divided by f prime of x1, it's f of x1 times basically 1 over the slope, where our estimated slope is found by taking the difference between x's and the difference between f of x's and difference between x's. Okay, so plugging all of that in, we're going to get x at the next iteration, n plus 1, is x at your current iteration times f of x at your current iteration times basically 1 over the slope, the approximated slope, which is the difference between x at time n and x at the previous time. And we've got that. Okay. So you plug that in, and so here's what code for this would look like. I guess I didn't write the code. Okay. But basically, convergence properties of the Newton-Raphson method is quite similar. And it will, if it's well behaved, it'll converge, and if it's not, we can't guarantee convergence. The trade-offs are you don't need to know the derivative f prime, but you do have to calculate kind of the values at 2 locations. Okay. All right, I think we're out of time for bisection method, and so we'll have to cover this later. And then we'll talk about approximating derivatives and whatnot. A new homework assignment will be posted. I know you guys are still working on homework 4 and Monopoly, but I'll post a new homework assignment that covers floating point numbers and some of these numeric methods. Some of you are already done. All right, so I've already seen your submissions. and some of you are still working on it. So anyway, if you're still working on homework 4, keep working on that. Good luck, and otherwise, have a great rest of your day. Have a happy Valentine's Day, and we'll see you on Wednesday.